Next, we'll look at example 15.7, which uses an Arrhenius plot to determine kinetic parameters. The decomposition of ozone, shown here, is important to many atmospheric reactions. Ozone, O3, forms O2 plus O. A study of the kinetics of the reaction results in the following data, so we see that shown here. Determine the value of the frequency factor and the activation energy for this reaction. So here we have the rate constant versus the temperature. So we see that the rate constant increases with increasing temperature. The Arrhenius equation can be broken down or rearranged to ln of k equals negative EA over R times 1 over T plus ln of A. And this is our y equals mx plus b, our linear equation. So for this equation, we're going to plot ln of k versus 1 over T. And we can get the frequency factor, ln of A, from the y-intercept. And we can get our activation energy, E sub A, from the slope, because the slope is equal to negative EA over R. So I'll just examine this problem with the solution given by Pearson. So to determine the frequency factor and activation energy, we have to prepare a graph of the natural log of the rate constant on the y-axis and 1 over the temperature in Kelvin on the x-axis. And we see here that we get y equals negative 112 times 10 to the 4th x plus 26.8, where 26.8 is our y-intercept, so that's equal to ln of A. And our slope is negative 1.12 times 10 to the 4th, which is equal to negative EA over R. So we can set our slope, negative 1.12 times 10 to the 4th, equal to negative EA over R. So our activation energy is given by 1.12 times 10 to the 4th times 8.314 joules per mole Kelvin. That's R in energy units. So our activation energy is equal to 93.1 kilojoules per mole. Next, we calculate the frequency factor A by setting the y-intercept equal to the ln of A. So 26.8 is equal to ln of A. So to get rid of the ln, we take e to the both sides, and we see that A is equal to e to the 26.8, which is equal to 4.36 times 10 to the 11. For practice 15.7 states, for the decomposition of ozone in example 15.7, use the results of the Arrhenius analysis to predict the rate constant at 298 Kelvin. So basically our temperature is 298 Kelvin, and we're going to solve for K. Our equation is ln of K equals negative EA over R, where negative EA over R is the slope, times 1 over the temperature in Kelvin plus ln of A. So we just need to plug in our new values. So the ln of K is equal to negative 1.12 times 10 to the 4th times 1 over 298 plus ln of A. So we have now, that ln of K, I forgot to plug my ln of A as the actual value here. That's 26.8. That was our intercept. So the ln of K is equal to negative 10.78. So I'll just move everything over here. So e to the ln of K is equal to e to the negative 10.78. And now we have K is equal to 2.07 times 10 to the negative 5th.